My name is Axel Fontaine, and for the next hour or so, we're going to be talking about logging in the age of microservices and the cloud. Now, an important reminder, as you may have noticed in the program, this talk has been marked as an introductory talk, so it is not a hardcore technical talk, so make sure this is what you're looking for. Over the next hour, we're going to be talking a lot about architecture, about principles, about best practices, but we won't go into the hardcore technical parts. So, let's first get to know each other. I would like to ask the people in the room here to let me know what type of infrastructure you're running on, so I kind of know what kind of audience to expect. So who is currently working on a project where you actually have your own data center, your own servers, you have everything in the basement somewhere of your company? Okay, so that's a pretty good proportion. We have maybe about 30%. Who has a project where you work on with co-located infrastructure? So you don't own the data center, but you own the server, and you have placed your server in somebody else's data center. Okay, so we have about 10% maybe. Who rents a root server somewhere? So you don't own the data center, you don't own the hardware, but you rent a server per month at some data center. We have, again, 5 to 10% of the hands. And who's on the cloud today? That's a good number. We have about 30% as well. Perfect. All right, so let's go back in time a bit and look at the good old days of logging. And we have our machine here, our physical hardware, and we have some kind of system running on there, and it's as it's running, it's producing log files. And when we want to access those log files, what do? Well, we SSH into that machine, and then eventually we'll do a tail-f, and we'll kind of look at the logs that are scrolling by, and all is pretty great. So that's actually a fantastic solution, and that's the end of my talk. Thank you very much. Don't forget to no, just kidding, just kidding. Let's look at it into a bit more detail. Let's look at the different parts that we have here and what kind of problems and challenges that we have. So first of all, this requires an open port in the production environment so that somebody can then log into that machine. You need credentials as well that you have to pass around to developers or to other people to access that production machine. We have a fixed host name here. We'll see why that is a problem later as well. Very often this is just stored as plain text on disk. It could be that there is some sensitive information in those log files as well, so we have to be careful. We have rather limited searching possibilities. We can kind of pipe this towards grep and kind of get some kind of help to pick the needle from the haystack, but it's not so easy. And we kind of have a fixed representation for our logging output as well. It's been produced in a certain way. The example here is just a default output from Spring Boot, for example, and that's basically what we get to consume later on as well. But times have changed a little bit, and in our new reality of the cloud and microservices, we actually have to let go of some of these old ways. So we're going to look at these two big changes in the way we design our applications, and we're going to look at the consequences of each of them to see what we must do to be able to deal with them. So we're going to start with the cloud. As we heard here in the room, I think we have about 30% that are already on the cloud. When it comes to moving to the cloud, you'll have a lot of vendors promising you that it's actually very easy. You just lift and shift, you take your existing application, you bring it to the cloud, and you're done. You press a button, that's it. But unfortunately, that's not really the case, because if you just do this, you actually create a number of problems. First of all, you place a lot of trust simply in your cloud provider. You could also get in trouble based on what kind of data is being handled with your application, whether you may be breaching some privacy laws there as well, so you have to be careful there. If you just use the cloud as a regular machine as well, you'll probably end up with a much higher bill than what you would have at if you were renting a root server at, let's say, Hetzner or OVH. And also, we're going to look into this into a bit more detail later. You have a very high risk of actually losing data when you're auto-scaling. So what are the fundamental changes that happen when you move to the cloud? First of all, we have a different security story. We're going to look at that in detail. We now have a cost-driven architecture. Again, we're going to dive into that as well. And we have auto-scale. To each of those in turn. First of all, security. To be able to understand security in the cloud, we must really understand the structure and the fabric of the cloud and how it's made. So at the highest level of abstraction, it's really a bunch of regions spread around the globe. And those regions, as previously mentioned as well, each come with their own legal systems. So this is something that has to be taken into account as well. Within a single region, if we zoom in a little bit, we have the concept of availability zones. Availability zones are one or more data centers within a specific geographic location. They're usually far enough apart that they're isolated from each other in case of natural disaster. I'm thinking about flooding or earthquakes or whatever you may have that could be impacting there, so that it's very unlikely that multiple availability zones would be taken offline at the same time. In this example here, the AWS region in Germany, for example, has data centers on different sides of Frankfurt. If we dive a bit deeper, we see that at the base of the cloud, the foundational services that are being offered are really building blocks that can be combined, and they really fall into three major categories. We've got storage, compute, and networking, and all of that is being encompassed by a security concept. And the security here is actually very different from the security that we're used to in the data center. For those of you that still have your own data center there, the security there is very much solved like in a medieval city, where you have the old city wall, and security is solved at the perimeter, where you may have your demilitarized zone, and then once you're in there, once you're inside the old city, once you're inside your data center, a lot of communication is unauthenticated, unencrypted. Systems can just talk to each other like that. And when you're in the cloud, the bad news is that this wall is gone. So you do not have that protection anymore, and you need to start thinking differently about how your systems will communicate. So a few hard truths about security. The first one is that there is no such thing as absolute security. It's always breakable if you have an infinite amount of time and resources, so you have to make sure that the prize, that the defenses that you put into the prize are high enough so that basically it's too complicated to make it worth it to break in. Security also comes at a price in terms of usability, because all those additional security measures usually will have some kind of impact on the user experience. And if we talk about security, it's very rare that it is about code. It is almost always about data. Let's face it, for many companies, they're barely able to compile their own software, so let alone somebody else from outside. It's virtually no chance. So it's almost always about the data. And the data has three main states. So first of all, there's data at rest, when it's actually stored on disk somewhere. There's data in use, when it's being processed in RAM. And there's data in motion, when it's being sent over the network. Now, a bit of wisdom from a very famous gentleman in the IT industry. Trusting your neighbors is good, but it's even better to put a good lock on the door. And this is very much what we have to do with our data as well. So the first one here, data in motion, actually sending things over the network. We have a fantastic solution available there. It's transport layer security, TLS, or often referred to as SSL as well. And it's 2017, so there is no excuse left whatsoever With Let's Encrypt, for example, you can have automatic certificate renewable, and it costs absolutely nothing. The same if you're on the AWS cloud. They offer something called the AWS Certificate Manager, and it integrates with elastic load balancers, and basically just takes care of all the certificate handling for you at no additional charge. So in 2017, no excuse to have unencrypted communication between systems. For data in use and data at rest, there the whole key is really to perform client-side encryption so that the encryption key is not co-located with the data, and then you can actually have a very strong story there. Now, cost is also a very important factor when working with the cloud, because if you work on your own data center, you basically purchased these machines a long time ago. It's a sunk cost. It doesn't matter how you utilize them. In the cloud, it's different. You actually have the potential, because you pay for what you use, to save a lot by only using what you need. So if we kind of look at compute here, for me, the essence really in terms of thinking about cost is that any kind of spare capacity is wasted money, because it's basically paying for things you're not currently using. So you have to really look at adjusting your capacity as closely to your needs all the time. And so the way to do that is through scaling what you actually use. So that's basically adjusting the capacity in response to a metric that will go above or below a certain threshold. So it's basically a corrective action in response to an alarm. So let's look at what kind of metrics we have available based on the type of services that we can build. So first of all, if we have a synchronous service, I think request response, some kind of REST API, for example, their CPU load, for example, on the machines is a good metric. The average CPU load over the last 60, 120, or 300 seconds is a good indicator there. Or if you have an asynchronous service, how many messages are piling up in the queue? Is this getting more and more? Should we add more workers or not? Or if you have some kind of time-based process, has the time ticked in where we're actually going to start firing this? So when it comes to scaling, we can scale in a bunch of directions. The first one we can do is scaling up, moving to bigger machines, or scaling down to smaller machines. We can also scale out more machines, or scale in less machines. Now in the cloud, we have this thing called auto-scaling. So what does that do? Well, basically, we've automated two different parts of this scaling story. First of all, we've created alarms that will be triggered automatically based on some conditions, and then we will take an automatic corrective action to be able to solve the problem. And so this corrective action involves adding or reducing the capacity that we currently have for our service, so scaling in or scaling out. If we look here, we have 3 machines. We have a load balancer, and we send the request. The requests get balanced over those 3 machines. We have applications running there. They produce some log files. If we want to access those log files, we've seen it. We can SSH into those machines if we want, tail-f, and then we can see the contents of those log files. Now, let's assume we have an average CPU load at the moment, and these are our thresholds that we've defined. If we have CPU load rising above this scale-out mark, it will be time to start adding machines to our system to reduce the CPU load to an acceptable level again. And if we drop below the scale-in mark, it means basically we have a lot of unused capacity. We're paying for things we're not using, so we should start shutting down machines as well. So, as we're processing requests, all of a sudden the CPU load rises. So what do? We scale out, we add another machine, and again we can access that machine like every other machine if we want to access the logs with SSH, and all is actually fine. After a while, because we've added the new machine, the CPU load reduces back to acceptable levels, all is happy. But now we're reaching the end of the workday. For example, a lot of people are going home and the load is dropping below our scale-in threshold. It means that basically we're paying for more capacity than we're actually using, so the auto-scaling processes will start taking capacity offline for example, this machine here. And so it means that everything that was on that machine will die together with that machine, including the log files that were stored on there. So this is very unsatisfactory. Besides, of course, all the problems of having to know onto which machine a specific user has landed and having to try all the different machines to find it. This is just one additional problem that's arising there. Luckily, we have very good solutions available in the form of centralized log service. And they're actually very mature these days and very powerful, and they give you a central place where you can aggregate all your logs. They're being stored and backupped, and you have a long retention, or you can configure it how you want. They're being indexed, so they're being made searchable. And this is a very, very powerful thing, because you can send your logs in real time there. You do not need to hunt on individual machines to find out where a request has landed and in which file it may have logged something. It's all in one place. It also means that in a modern data center with a fast network, you can send the logs in real time. There's not even need to buffer them on disk, so you can just send them via HTTPS to the log server, and you're done. And we actually have a good number of very mature products, both for the on-prem and for the cloud. There's things that you can do yourself, like Logstash and an ELK stack. Or if you're on the cloud, you can use on AWS, for example, the CloudWatch log service, or independent services like Loggly and Papertrail. And they're actually pretty powerful. Like, for example, Loggly, they'll supply you with an XML snippet if you use Logback or Log4j that you can just copy-paste into your Logback or Log4j configuration, restart your application, and it starts sending the logs out there. So it's really incredibly easy to use, and this is something, regardless of the type of infrastructure that you use, that you should really be adopting today. Now, microservices. Let's see what kind of infrastructure everybody has in the room here. So who is currently running on some kind of integrated system or monolith where you have mostly just one main deliverable? Let's see, we have a good 25% maybe of the hands. And who is running on a distributed system or microservices? The vast majority, we have about 3/4 of the hands up. Very good. Okay. Let's take a step back and ask the question, why we're actually doing this logging? Why are we going through the effort to do that? And the answer is really to be able to perform post-mortem analysis of user activity and programming errors. So post-mortem is really just another word for after the fact, because we're usually not tracing it live on a production machine. It is possible, but very often we want to understand if a user has reported some kind of problem with the system. We want to be able to find out exactly what happened and what was the context at the time that happened. So this is really quite a powerful debugging tool, and it lets us ask important questions about the system in the past. What was happening and who was using it, and where did this problem occur and when did it occur? And so these questions are really important, and we can answer them by providing some context in our logs, some additional information. So the what is actually quite easy. This is our logging message with maybe an error code and some severity like info or warn or error. The who, that is which user was currently using the system, which account, what was the current session that was being run there, or which request was being processed. The where is if I have a distributed application, in which service did this actually happen, or within a larger service, in which module or in which class. And the when is, at what time, on what physical machine as part of that cluster, on what process that was running there, what thread, so we kind of know exactly where this happened. But to find out this information is one thing, but you have to actually be able to pass it to the logs. So how can you actually provide all this information to a log statement without having totally unreadable code and something that's difficult to maintain? And if we do that, then how can we then ask the right questions to our logging system to be able to find those answers? And because we'll be investigating some things, and we're going to be wanting to ask those questions, but how can we do it? So we're going to first focus on capturing logging information. If we look at the architecture of popular logging frameworks, they're all quite similar. It's basically quite easy. On the JVM, all the logging frameworks were designed by the same guy. It's Seiki Gulku. I'm not sure if my pronunciation is correct, but it's basically the guy that basically designed them all. So they all follow the same architecture. If you have your code will talk to a logger. A logger will then forward the message to a number of appenders that can be configured in your configuration file, and each appender will then forward the message to some kind of storage that it has behind where it can do those things. So what can those appenders be, for example? Well, here are just two quick examples. One could be some file appender or some rolling file appender where you have one or more text files that are being written to disk, or you could have an appender that talks to a log server and basically sends the log messages over the network to the log server. Now, when we write the simple statement where we log a simple message, what kind of information are we actually passing there to our logging framework, or what kind of information is available to our logging framework? If we look at the different questions that we can ask, we definitely have a few that are answered and a few that are not. So for example, here we absolutely have a logging message. We can optionally include a code as well. We see the severity as part of the method that we're executing. It's not immediately clear which user is actually interacting with the system or caused this to happen, or which request or which session. We don't really know which application is emitting this or which module, but we can, through our environment, find out what the current time is of the system, what the current host name is of the system, the current process ID, the current thread. Those things are things we can discover. So we have some information that we have available, and we have other information that we're currently still missing. So we need to find a way to acquire that information as well. To be able to do that, we can use another facility that's available for every single logging framework out there. And that's the MDC. MDC is an abbreviation for the Mapped Diagnostic Context. It's basically a facility available in Log4j and Logbag, also abstracted via SLF4j, where you have the opportunity to store key value pairs in a thread local store. So that is values that will only be visible from the current thread, and you can store them whenever you like, and you can take them out again when you like. And so this allows the code to interact with the logging framework via a different channel as well. Because if you have a request that's executing, every log statement while that request is executing will need the same information about this is the current request or this is the current user. So there is no need to pass it with every single call to a log.info. Instead, we can set it once in the MDC. So this will typically happen once once a request is entering the system. There's a few more scenarios. We'll look at them into detail as well. And then once it's stored in the MDC and the code triggers the logger to actually log something, then the appender will pull information from the MDC, and we'll be able to combine all that and send the information to the along with the rest of the message to the storage. So how can one use the MDC? It's actually pretty simple. It's basically just it looks like a map to the outside world, so you can just use the put operation, and then you can place a couple of keys and values in there for what you need. So in this case here, this example, we're just recording that the current account interacting with our system on this thread, it's thread local, is company ABC, and the current user for that account is user 123. And this is quite powerful, because now, all of a sudden, we can record this information, whatever information we care about in our system, and we can answer the who and where questions as well, so that we can then, if we combine that with actually logging all that, we can actually answer all those questions, because when logger.info will be executed, again, the appender will have access to the information that's been put in the MDC and can recombine all that, and we can actually have the whole context to be able to answer those important questions. So what's a good place to be executing those statements, those put statements to actually place something in the MDC? The first obvious one is when a request enters the application. When you have some kind of controller for your application, a web or a REST controller that enters the application, then you will typically have a request which you can assign a unique ID that you can then place into the MDC. You maybe have a session as well, which you can also record the ID in the MDC. Through that session, you may be able to find out which account or which user is currently logged into the system. So this is, again, information that you can record in the MDC at that point. But that's not the only place, because the system can be triggered through a number of ways. So again, if you have some kind of asynchronous processing where you're picking messages of a queue on different worker nodes or worker threads, it's that kind of information as well. So you need to kind of have some to again generate request IDs, for example, or message IDs that you can then place in there, so you can then trace the whole logs that were related to the processing of a specific message all through the system and the various systems downstream. The same thing, one more thing to watch out for as well, is if you use things like Spring and asynchronous programming. They make it really easy. You just add an async annotation, and then you have a different thread that will be spawned once you execute that method. Again, different thread. The thread local variables that we said before will not be visible, so you need to transfer those to the new thread and set them there as well, so that that information is recorded there as well. And very important, it's important to clear those things as well once you're done using them. So once the thread terminates, or the request, or the execution gets to the end of its natural flow, or you're sending the response back to the client, you have to actually clear the MDC as well, because there's a lot of thread reuse in an application. You have a lot of cases where thread pools are being used, and so it's very possible that you could get some dirty state in the MDC for a next thread. So you have to kind of clean up after yourself, and you can defensively, if you start a new request, also fully clear the MDC as well. So then you're sure that you don't have any leftovers from a previous invocation. Now, it's one thing to put things in the log, but the value is only realized, of course, once you can also ask those questions against the logs and find out what is actually in there. So if we have our little example here again with a default layout of what's being produced by Spring Boot, for example, how can we actually search this? We've already seen grep. Possible, but not ideal, because we actually have a number of issues here. First of all, as we can see, we've got some information that's being truncated because we've got some kind of fixed layout to make it look nice in the console or on screen. So we've got like fixed widths for our columns, and if something exceeds the width of that column, then we have to truncate it, or alternatively, there is some compression being used, in this case here, for the package names that are being shortened for our classes. So there again, we try really to fit within the certain specific number of columns that have been configured in the layout for this. This also only looks good if we are dealing with single line messages. As soon as we have output that's spanning multiple lines with some new lines in there, the whole layout is kind of messed up, so it's not that great either to kind of look at. And we do have some context information, but we're still missing a bit as well, and we don't have any information from our NDC, which we discussed before. So this would have to be altered to put it in there. So there's a whole bunch of things that don't make it really easy to kind of search for this, even if you want to search for a specific thread ID, as you've seen or you can maybe see in the last line of the output there. There's possible that there's square brackets, for example, in this case, also being used in the regular output of the logs, and so kind of matching those is kind of risky as well. You get a lot of false positives as well. So it's so really not ideal. A whole bunch of little problems that add up. And so to be able to solve those, we kind of have to take a fundamental step here, and that's decoupling log storage from log representation. Because what we've been doing so far is really kind of putting everything together and pre-formatting it in one go. And so if you kind of look at our little flow that we had, and where our code is talking to a logger and storing some information in the MDC, and then the appender is being triggered and accessing the MDC, and then what's happening? Then very often we have in Log4j or Logback something called the layout that will then take this information and then flatten it into a line of text that will then be sent to the storage. So we have this formatting happening very early in the process, and basically irreversible. Whatever information has been truncated cannot be safely reconstructed later. It's gone. And so whatever log viewer we have at the end that will be accessing the storage there, whether it's just a VI or whether it's some kind of REST client for a log server, we are only able to read what was written in that specific format at the time. So this is a clear weakness, and we have to resolve this. And so we have to try to delay the formatting as late as possible, so that in formatted log messages, we're going to store raw messages in a format that lets us later read them as we wish, and then place them in the format there, because it's always possible to do this step of actually formatting like the Spring Boot default output if you have access to the raw data. But the way back is not possible anymore. So this is something where we're going to be looking at adding some, delaying that as much as possible. And the answer to that is really structured logging. So it's moving away from just plain text and some specific fixed width type of columns into something that has a structure that is then able to be processed later. So we have a number of data formats that are very widely used across the industry, where there are parsers and emitters for a whole bunch of languages. This is JSON and YAML are very good examples. This is a JSON example where this would be the contents of a log message. So we would have a bunch of key value pairs that we would store, where we would have, in this case here, an account and some message and some request ID and some session ID and a timestamp. And we kind of store all this information together. So we have part of the invocation from the logger, we have part of things from the MDC, and we kind of bring all this together. The nice thing is that if we can, from this, reconstruct a representation like what we had with the default Spring Boot output, that's no problem. But the nice thing is also that we now have something that's machine readable. It is much easier to parse, and in fact, it's even more than machine readable. This is actually very powerful, because it's actually machine queryable, where we can start asking questions, where we can ask what is the contents of this specific field and be able to answer those questions quite reliably. So what do those questions actually look like? I've got an example here with CloudWatch Logs on AWS. It has a specific query language for those. All the different tools available have their own kind of syntax. This is just to illustrate. So for example, there it's possible to query the logs like this, where you would have some kind of, it's their own kind of little DSL for being able to do that. And in this case, you would look into the log message, and then from the root of the message, you would look at the account key, and it would have to match exactly that specific string over there, and you would have to, and you combine this with a separate condition that again from the root of the log message you look for the request key, and that would have to match exactly, for example, this specific request. And so the little DSL that they have is actually quite powerful, where you can do some kind of like matching, like you would have in a database as well. So it kind of allows you to search on specific parts of messages or things where you do not have maybe a well-defined key. So this is a powerful thing to have, and this can of course be hidden behind a more convenient client with a nice UI to be able to do that. But you have some kind of API available so that the logs are machine queryable there. Now, if we have multiple independent services talking to each other, at the end of the day, they're all kind of sending data to the log server as well. And it's very, very important when we have all these different services there to be able to query across service boundary as well, so that we can actually trace a request from a specific user across all the systems where it actually passed through, that all the interactions that were caused there. So to be able to do that, we have to watch out for a few things as well. When a request enters our system, it will follow a specific path of for going from one machine, talking to the next one, that may be querying further machines downstream. And so we have some kind of interaction between those systems, and we have some bits of information that we should really be passing along. This is all about propagating what we put in the MDC, where we store this information about the current user, about the current request, about the current session, so that we're then able to have a consistent view across all those systems. So how does this work? Well, usually in the first system where the client is interacting, we'll create the initial MDC data. If we already have a session, we can use a session ID, and from that we can derive users and accounts and all kinds of things that we can use there. We can assign a unique request ID that will then be valid through all the systems we're going to be talking with. And once we've combined all that information, we're then able to use it internally. And if we start making calls to external systems, we then have to somehow propagate that information. And so the easiest to do that is really to copy the different attributes that we have there from the MDC into headers of an HTTP request, so that you can then have some kind of prefix, for example, MDC dash and then the name of the key in the MDC, and then you put all those headers in. And once that's been a part of the request and being sent out to System B can then, on its end, as it's receiving the request, read all those headers and again copy the information back into the MDC, so it can then use all that locally, and all the log statements being issued as part of System B will then have all the necessary context information. And the exact same thing happens when we communicate with System C. We once again copy it all in the headers, and then C reads it out again. So we basically have a combination of two things here that we're doing. On the one hand, we're filtering incoming requests for bits of data that we're using, and then and this can typically be solved in a servlet filter, for example, on the JVM, so that we're intercepting that all in one place for all the code, and we're putting it in the MDC, and as we're about to communicate with the next system, there you can have some kind of decorator. Let's say if you're using something like the Apache HTTP client, you can decorate the connection creation, the request creation for GET and POST requests, for example, so that you automatically add those headers, and then that kind of continues the other way. And in the next system, the same things happen. The filter is then able to automatically extract all that and again, you decorate on the other end. So it's possible to solve this centrally with very little code and very effectively. The only thing that you have to watch out is if you have multiple programming languages, multiple platforms, you have to be sure that those things are replicated exactly. Otherwise, if you're on the same platform, then you can just create a shared library that is being imported by the different services, and that you can then use the same everywhere. But that's not quite enough just yet, because when different systems will start sending log data to the centralized log server, and we have our key value pairs that are being sent there, but it's actually very important that we focus on having a standardized naming for our keys, because if one system sends the request ID as request and the other just sends it as request ID and then REQ, maybe a third system, it becomes very, very difficult to ask questions to our logging system that span more than one service. So these keys need to be standardized across the entire microservices landscape, so that every system that is in there will use the exact same terminology. So you define this once for the whole company, and you're done. Very often, the actual amount of keys that you will need to define is not infinite. It's as we were talking before with the questions of what, where, when. It's usually the same bits of information that you want to record, and it'll be something in the order of 5 or 10 or whatever works for your specific context there. That will be relevant here to standardize. But that's not entirely enough either, because just having the keys standardized still makes it difficult to do some kind of matching. For example, if you look here at the log level, if we for the message, if we have info here, maybe it's info that one system will send it in small letters, the other one will send it in capitals, or if it's a warning, it could be sent as warning, as warn, as a W. So you need to actually standardize the values of those key values there as well. So because different logging frameworks will probably come with different things there as well. So you have to be careful that all that gets transformed to some unified format. The same, for example, for the timestamp. If you want to be able to search for specific ranges of timestamps, or it's important to have one kind of format. And this is this is just a standard ISO notation, but you could use the epoch time as well, since the Unix time. This is something that you can choose. It doesn't matter. At the end, the main point is that you have to standardize on one main representation. And so the same for your request, for your session ID, you have to make sure it's kind of replicated exactly. All right. If we summarize all this, we've seen that it is not just a nice thing anymore. It's actually a necessity in the world of the cloud to send all your logs to a centralized service. Machines may come and go at any time. If you think in the world of auto-scaling, where certain triggers are being fired once you exceed certain metrics, CPU load or queue depth, machines may come and go. So you have to use a centralized log service. We're in luck. There are many mature solutions on the market, both for on-prem and for the cloud, so you just pick one. Any solution there is much better than just sticking to plain files. Decoupling the representation of our log files is a very powerful enabler, so trying to format as late as possible in the process, more when you're actually getting ready to display the log files instead of getting ready to store them, and store the log files in a structured format that is then not only machine readable but also machine queryable. For additional information and context to be able to answer the important questions that we raised earlier, to be able to have the necessary information when you're investigating what happened with a system, you have access to the MDC, which lets you reduce the amount of code that you need to write with every logging statement, because you can just put it in one place. But this is also something that you have to propagate between systems. So take care of that. Look, if you are all on the JVM, for example, to have one standard library that you use for the decorating HTTP client requests that you're sending out, and a standard filter for consuming things that are coming in. This is reasonably easy to develop. Standardize both keys and values. Just the keys is not enough. It's a very important start across services, across frameworks, across languages. But the values are important as well. Think about our log levels, about the different things that we mentioned. And once you have all those things in place, then you have actually a very powerful set of tools available to ask those what, who, where, when questions against your log files, and to really be able to, for example, trace this exact session from that one user across all the different systems, and be able to match messages with a specific keyword in there within that session exactly, and get those answers there. And for example, with AWS CloudWatch logs, the performance is excellent, so you can, against very large log data sets, ask those questions and get answers within milliseconds. So this is really a very powerful thing to have at your disposal there. So who am I? My name is, as I mentioned in the beginning, is Axel Fontaine. Some of you may know me through some of my projects. I'm the founder of a company called BoxFuse. I also make an open source project called Flyway. I'm a Java champion and a Java 1 rockstar. Flyway is an open source tool that's quite widespread, that some of you are certainly using already, that is there to evolve the schema of relational databases. It's being made so that you can do this reliably across all your different environments and database instances. It supports most of the, or almost all of the popular relational databases, and it is open source. There is commercial support available if your company needs that. And it's currently a very wide base. I think this year we'll probably pass 4 million downloads, so it is very, very widespread on the market. The other product that we make is BoxFuse. It's very close to the talk that we did, that you just listened to today. We specialize in deploying JVM applications to AWS. We also support Node and Go applications. We have very specific support for lots of frameworks as well, like Spring Boot and Drop Wizard, or just plain Tomcat or Java. This whole thing works by using immutable infrastructure and minimal images, so it's really very, very tiny. These are images that are maybe 30, 40 megabytes in size and generated within seconds. You can run them locally on VirtualBox or Hyper-V and deploy them with zero downtime on AWS. So basically all this is kind of taken care of for you, so you can just push this out. And we have first-class support for centralized logging with AWS CloudWatch logs. So the questions that you can ask, the things that we mentioned before, we have a very easy CLI to be able to ask those things in a console and get access to them. We have appenders that take care of all the heavy lifting of what you saw before as well. So that's all I have for today. Thank you very much for your time. We do have a number of minutes available till the 60-second mark, but...
Yes, hi, I'm the track owner, and I will use my position maybe, and we'll ask you to answer a question that came online.
Okay, so I'm going to read the question first. Yes, we have ELK stack or Graylog for gathering login data on production and testing clusters. However, developer is still using SSH, tail, grep when developing and local testing. Is there any log gathering tool which is lightweight enough to use on a developer machine? So here I think there's different options. I think these days we're quite in luck that first of all, developer machines are getting quite powerful. And the days are over where we just had 1 or 2 gigabytes of RAM. It's very common to have machines with 16 gigabytes of RAM or more. And all the machines that you have on the market today are multi-core. It is, by definition, impossible to buy a single core machine on the market anymore. So those are very nice opportunities where with tools like Docker, for example, it's very easy to fire up some of those servers in a non-clustered configuration locally and just redirect your application at the IP address of the local container, for example, that has started. Alternatively, because those things are transparent to your code, because it basically resides in your logback.xml or log4j.xml, or if you configure it, then it is actually possible to swap out the appender very easily. So you could, on certain environments, have the appender push things out to an actual logging server, and on your local environment for tests, for example, still use a regular console appender so that you see things there in real time. So this is definitely something that has no impact on the code. It's just a bit of configuration change. Again, I think when having to choose, it is preferable to keep all environments as identical as possible. So to use actually the same tools for gathering logs in the development environment as you would in the production environment. But if that is somehow a limitation, then this option to move to a different appender is possible as well. Yes?
Yeah, let's talk big scale. Let's say we have a big distributed system is generating like tens of gigabytes of logs every day, and we want long-time retention. Usually, I mean, we are using Elasticsearch and ElkStack, but it can't work with. So if you have like tens of gigabytes every day, we can, I don't know, keep logs for a week or maybe 2 weeks, but 2 weeks are not enough to get like, long time, I don't know, correlations. So have you had any experience with deployments of that scale? And if you had, which basically logging solution can you find like suitable for this scale?
Okay, so I think that the first thing here is really log retention. That's an important point. The value of logs decreases exponentially with time. It is very interesting to find out what happened in the system 1 hour ago or yesterday or even this week. Exactly what happened a year ago, not so interesting anymore. Why? Because the code that will be running will be completely different. Some of the interactions will be completely different in those log files. And so certainly as you move to a more rapid pace of delivery, the rate of change will increase as well in the code there. So this is some kind of trade-off to make there as well. It may, even though it may seem attractive to go for a very long retention, the question is, do you even need it, or can you actually live with something less? An alternative could be also to post-process your logs and to use some kind of high watermark, where if you associate, for example, like we talked here, your logs with a specific request IDs or sessions, you could then just choose to maintain for longer term only the logs that have a log message above a certain threshold. So only a log output that from a session that had at least a warning or at least an error, and you discard all the good cases because those are probably not things you will need to debug or research later. And so you can actually have longer retention while reducing the volume, and most of the off-the-shelf tools will actually let you deal with that because you don't scale to infinity with the amount of data that you retain.
Okay. Well, what are the cons of your FlyAway-DB?
Pardon?
What are the disadvantages of your FlyAway-DB?
I think this could lead to a longer discussion, and we have room in the discussion room later. So we can talk all we want about FlyAway then. I think for the next few minutes we'll go on questions for logging, and then we can talk about FlyAway or Boxuse in the other room.
So we have a bunch of different solutions for logging in some clusters centralization in our infrastructure. We use, for example, Splunk, Elastic, and other services, and all of them have a kind of different gap because they have taken enough time to make some indexes and how to make in-time monitoring, in-time logging monitoring, because you said that cost of the data, cost of logs increasing exponentially from the time, and we sometimes need to find the bugs right now. What's the problem with our infrastructure?
I'm afraid I didn't fully understand your question, but we can let's take it offline in the discussion room, and then we'll. Yeah, I think there's one more question at the back. We have time. I think we have a few minutes. Yes.
Thank you for the talk. My question is about the appenders that you show. So our experience was that the appenders was not actually, they were not good because if your application dies, it means that all the appenders dies well and you have no logs now. And it's better to stream to SD output, STD error, and just have a service collecting all this stuff and streaming into Elk, Splunk, or wherever other things. At the same time, it's easy to start up to launch your application locally on your local machine, or if you need to deploy it in the clouds, you can do it quite easily because you still got it. But you need to have something like, you just don't need infrastructure, you need a platform that can do this for you. And my point is about that only, the appenders that they don't work well sometimes. It's better to stream to SD output error and collect all this data, but because anyway, if your app dies, you need information about the application anyways, about your environment, what was happening at that very moment and what's going on there. So it's like the first approach that you can take, which you can use, is very simple, but after that you should think about the platform itself and how you do logging and other stuff. So it's not a question, sorry, just another opinion, another point of view. Thank you.
All right, well, but I agree. I think it's definitely the two alternatives that you have, either to kind of use your logging framework and the appenders that you have, or kind of have the kind of logging agent on the node, or as part of the platform as a service that will then just kind of slurp up whatever you throw at it on standard out and standard error and pass it on. So those are definitely two valuable options. Yes.
So I'm sorry, we have just a couple of minutes left, so maybe just a couple of last questions.
Hi, thank you for speech. I have a question about changing log level at runtime when you have an example Java application and you have some log level, but when things going not well, I don't know, maybe warnings comes out or something like that, errors, do you change log level to lower? For maybe high load issues, so you don't need so many logs when you're good, and when bad things starting, you need a lower log level. And how do you do these things, changing log level at runtime, and how do you do it if you do?
Sure. So in terms of adjusting the log level at runtime, let's first look at the kind of filtering with the log level. In an ideal world, under ideal conditions, you wouldn't need this. You would just store all the logs from everything, and then later you would just pick whatever you want. But then we run into some specific constraints of what's actually possible. Some frameworks produce way too many logs, and it's always a success, and it's actually not worth to retain it, so we can raise the log level higher to have those things. And so in terms of having this as a runtime configuration option for some of your code or some of the framework code that you use there, again, if you can avoid it, if you can just store all the logs for a specific period of time, regardless of the log level, go for that. If that's not an issue, if that's not a possibility, then those are kind of ways to work around that. But it's always a risk, of course, that if you raise the log level too high, you miss important clues in the lower level logs that you may not have available if some kind of problem happens during that time frame. So this is something that you need to balance. It's kind of a risk on the one hand with kind of saving on the other hand in terms of performance, in terms of amounts of data. So this is something that has to be evaluated. The classic IT answer, it depends. So we're out of time. Thank you very much for attending. We're going to be walking to the
discussion zone number 3.
Yes.